most of people are using the internet, right? It might get slow also. So just let me know, do update if my voice is not clear, and then I'll make sure to cover that again. Okay,
Definitely.
so yeah, so yeah, I'm working here at University of Arkansas at Little Rock. Pardon?
A participant kindly requesting to mute your mic.
Yeah, I'm getting a lot of noise. If you have any questions, don't hesitate. Just feel free to ask me, and I would be happy to answer that during the session. Or else at the end we'll have a question answer session. All right. So good morning, all. I'm Ashok Kumar Sharma. I work at University of Arkansas at Little Rock here in USA, and involved in teaching mechanical engineering courses. With that, I'm also involved in research and development work in the biomass thermochemical conversion areas. So I welcome you all for my presentation today on catalytic hydropyrolysis of biomass lignin. So before I come to this main topic, my goal is to give you necessary enough introduction on this area. Particularly, more emphasis will be on biomass pyrolysis. I will cover. I'll give you some information on biomass thermochemical conversions, different processes, and then somewhat in more detail on pyrolysis, and then current challenges in these areas and goals and objectives of my research. I have been involved in this area more than over 16 years now. Had opportunity to work in the different areas, including combustion, gasification, pyrolysis, somewhat on solvolysis also. So these are the different areas that I have been working. So I'll give you the overview on various goals and objectives that I have been working on. And then as the topic of this presentation, I'm going to cover one of my research study on lignin pyrolysis. So that would be the focus of today's presentation. So biomass, there are several options available now for biomass. For example, agricultural residues, and then the forest residues, energy crops, even municipal solid waste. Mainly the organic part contain of the municipal solid waste. There are researchers now we define as under the classification of biomass. So it can be also used for energy production. Sewage sludge. Yeah, any question? Yeah, I got some sound. Is there any question? All right. So sewage sludge, right? It has several organic components, so that can be used as a biomass, as a source of biomass. Microalgae, a lot of research going on microalgae, so that is also one of the source as a biomass. So biomass has several benefits. Let's go through one by one for those benefits. So first of all, it is a renewable source. Most of these are a renewable source, and then it is available on a sustainable basis, because one of the concern also that when we get the really good hands-on technology wise, or when we get the mastery on some process, we need the input resources, for example in this case biomass resources. So sustainability is one of the important consideration, because how we are going to obtain the required amount of biomass on regular basis. So most of this biomass are available in a required quantity on sustainable basis. So it addresses it has a benefit of on these aspects. Then most of this biomass are carbon neutral, meaning that it's not when we use it and develop the produce the fuels, and when we use that fuel for let's say for energy production, power production, or in transportation section, right, as a engine fuels, for example, whatever emissions we are creating, the carbon emissions, it is not going to add that carbon because it is derived from the plants, trees, all those organic compound, which is a part of the cycle. So it's not going to add the additional carbon. Those carbons are already there in the environment, and when the plant grows, it consumes those carbon, and then we are putting it back to the atmosphere. So it's kind of close a cycle, and that's why it is categorized as carbon neutral. In compared to that, when we use the fossil fuel based fuels, we add carbon to the atmosphere. So that's not the carbon neutral, but biomass, yes, it is a carbon neutral. Then another benefit is that most of this biomass accepts the MSW, which has some disadvantages also, considering the environmental point of view. But other biomass are eco-friendly. It's not harming the environment. Again, it can help us to address the energy security. So think about with the growing population of the world, how we are going to meet the energy demand right in the upcoming future. So considering that biomass, if we can convert these different available biomass for the energy production, it can supplement part of the energy requirement for the current and future needs, and that way it can help to support the energy security. So that's one of the good benefit of biomass resources. It can also help the economy. Though this biomass resources, most of this feedstock have lower prices. It's not that costly. But again, when you purchase it from different sources, at least there is a transaction, right? Money is involved, and it can help building the bioeconomy in this area. And then, of course, in biomass handling, biomass pretreatment, biomass conversion, biomass utilization, right? There are different stages. So all the stages, manpower will be involved, and it can help creating many employments in this area. So that's what the bioenergy sector can contribute by utilizing different bioresources. How there are several issues are there. I'm not covering all, but some of the important issues, particularly with the MSW, right? So municipal solid waste, most of the places, what we do it landfilling. So we fill it on the land, and it can keep piling up on those areas, and basically then it contaminates it contaminate there is a contamination of the air, land, and water. Okay, so this even landfilling is also not going to help, particularly with the MSW, which has a lot of plastics or those material which needs a really good amount of time and the process condition to degrade, because biomass is likely to degrade in some time, but this plastics takes a lot of time, right? And then it needs particular conditions for degradation. So that's the reason this MSW landfilling, wherever we do that, it's contaminate that part of the land and air and water. And greenhouse gas emissions, right? We all are aware of that. It's keep going on, and there are several tasks are now in this direction, right? Several countries are focusing how we can reduce greenhouse gases. So utilization of different biomass resources can contribute because it's a carbon neutral, and that's going to give the reduction in the overall greenhouse gases over the time. Again, that depends on the how much we are utilizing these different resources for the energy production or biofuels and bio-based product. So we can define the biomass composition or biomass based on the proximate analysis, or we can do the ultimate analysis where we can give the composition of biomass based on carbon, hydrogen, oxygen, nitrogen, and sulfur. Uh, or we can go, as I mentioned before, the proximate, which can. Yes, any question? Okay, so we can give based on the proximate analysis, right? Which is the how much volatile content is there, how much fixed carbon is there in the biomass, or how much the ash content is there in the biomass, or how much moisture, right? Most of the time, when we get the biomass, it has typical moisture content that could vary from 10 to 30%, or even more, depending on the source of biomass. Other than that, biomass composition can be defined in terms of those organic compounds, for example, cellulose, hemicellulose, and lignin. So these are the typical formula for these three organic compounds present in the biomass. This is the example of typical for wood as biomass. And this composition varies from type to type biomass. So if it is for wood, if it is from some grassy material, for example, switchgrass, it is going to be different. In case of the organic compound of municipal solid waste, it is a mixture, so it might have different composition of cellulose, hemicellulose, and lignin. So these are the three primary organic compound present in the biomass. And if you compare, there is even in the wood also, there is a hardwood and softwood. And if you see the distribution of these three compounds, these are not same. For example, in a hardwood, cellulose is 43%, while in the softwood it is almost the same 43%, right? While hemicellulose, it is very high in hardwood as compared to softwood, which is 28% in the softwood. And then lignin content, which is one of my study I will cover today, lignin conversion. We can see that in the hardwood it is 23%, while in the softwood it is 29%. So slightly higher, not slightly, it's significant higher in case of softwood, the lignin composition. So let me give you some overview on different biomass thermochemical conversion processes. So I'm not covering all. There are several if you go to the main classification and then sub-classification. But I'm going to cover the primary three classifications under this category. So before that, let me give you some more information here. So when you see the green arrow, that's going to indicate the inputs, the raw material that is going to be supplied as an input to that particular process, while the blue arrow indicates the main product from that process, and the dotted arrow here that will indicate the byproduct from that particular process. So biomass can be converted to different fuels, maybe in bioenergy or biopower or thermal, right, for heat generation, or for biofuels, which is advanced fuels, or for biochemicals, or for bioproducts. So, for example, carbon fiber. That's a good example that we can get it from biomass. So biomass can be converted through this primary three processes. There are several others, as I mentioned, but I'm going to focus on these three. So for example, pyrolysis, gasification, and then combustion. So in pyrolysis, the process takes place in the temperature range between 300 to 600 degrees C. And then in this process, the primary product is going to be bio oil. So we get bio oil. It's kind of very similar to like the crude oil. but has dissimilar properties when we compare with the crude oil. And then it has a biochar, so that's a solid product. It has a good carbon in that, and this product, this solid char, can be used for to generate the activated carbon for filtration process, or we can use this biochar for soil amendment. We can add that into soil to enrich the soil properties. I'll come on the biofuel, the bio oil utilization, right? So bio oil, which has it has many compounds in that, from lighter to more complex compounds, and it's not that suitable for direct use in the as a gasoline, in the gasoline engine, or which is a petrol engine, or even for the diesel engine also. We need to purify that. Basically, we need to clean it, we need to upgrade it. So there is several upgrading process with and without catalyst that many researchers have been working on that. They have done different studies, and then we have a really good data on that side also. So, and then there is another byproduct we get from this process, which from pyrolysis, as gas, which is also known as producer gas or seen gas. The seen gas has hydrogen and carbon monoxide and some methane as the primary constituents of the gas, which has a good combustible value. When we burn it, we get a good amount of heat. So we can use that heat to supply part of the heat for the pyrolysis process, or we can use that heat for some other application. Right, there are many applications on where they have used for combined heat and power applications. So CHP application is one of the good example where we can use for this heat for power and heating purpose. Then the second technology here is the gasification. In this process, uh, this process occurs at the temperature in between from 500 to 1300 degrees C. And then there are different gasification reactors are there, different designs, different processes also. So based on the type of gasification process, type of reactor, they employ the operating temperature for that. So in this range, gasification process occurs, and where we feed the biomass as input. And in this process, I have not mentioned before, but pyrolysis process, we do need to supply the gas, which is inert gas. It is not participating, for example, nitrogen. So nitrogen will supply the nitrogen to the pyrolysis reactor, and it takes the all the vapor product with it, and then we can condense that those vapors in the form of bio oil. So we need inert gas in case of pyrolysis process, which is mostly researchers has used nitrogen. Helium is also one of the options, and some have used nitrogen plus some hydrogen to improve the bio oil property. And there has been recently few studies available in the literature that people have also used supplied some air or oxygen, just to provide some oxygen to supplement the part of the heat. So they call it oxidative pyrolysis in that case. But in general, for pyrolysis, we supply biomass and inert gas, mostly nitrogen, for this process. In case of gasification, we do supply biomass, then we need to supply oxidizing agent. It could be air alone, it could be oxygen, or it could be a mixture of air and oxygen, or it could be a mixture of steam, or it can be a mixture of steam, air, oxygen, or steam, oxygen, right? There could be several combination. So basically we supply that because steam, air, oxygen all has oxygen in that, and we need oxygen for gasification process. So basically, in other words, gasification is defined as the partial combustion. It's not complete combustion, it's a partial combustion, or you can say limited combustion, right? So we will not burn the biomass completely, but in place of that, we will supply a partial amount of oxygen in terms of air, steam, or oxygen, pure oxygen, uh, to partially burn it. And when we do that at this high temperature, biomass through gasification produces primarily produces gas, which is known as syngas as the main product. In this process, we do have biochar as byproduct, and we do have a tar, which is not good. That there have been several studies on how on tar removal process, right? That's one contaminant, right? One of the main contaminant, right, which we don't want in the syngas, but as a part of the process, we will always have tar. So then basically tar clogs the pipeline, downstream pipeline, reactor pipelines, which is not good because then it increases the maintenance of the system. Over the time, this tar also form the scaling of the metallic reactor, and then falling of the reactor, the layer will fall over the time, and then it will probably a time will come that in that case we need to replace the part of the reactor also. So basically tar is not good. It's a contaminant, and we need to minimize it as possible during the gasification process. Okay, so we get syngas as the main product in this process, where we need steam or air or oxygen for the process. The third process is combustion, and here this process generally takes place in between 700 to 1400 degrees C temperature. And here we supply the biomass, and then we do supply air, oxygen for this process. So we burn it. In the combustion process, we make sure to supply the stoichiometric requirement for complete combustion, right? Just to maintain, ensure that the combustion should go to 100%, we do supply excess air. So when we do combustion calculation for a particular fuel feedstock, we add always some excess air, right? 10 to 13% excess air in that, just to make sure that the particle will completely burn, and it will give the maximum heat, which is the main product through this combustion process. And then combustion process, since we are burning all of the organic compound, the combustible part of the biomass, the residual is going to be ash, which is mineral oxides, depending on the type of biomass. So that's the byproduct. And there has been ash also has some properties, or it can be used in the refractory industries, or it may have some other properties for some other application that one can use it. There are some studies also available where which is focused on the ash utilization of the ash. So I hope it's now clear the differences between this three primary thermochemical conversion technology, and how we can convert biomass into desired product, whether liquid product. If you want liquid fuel, then the pyrolysis is going to be the better route, because we get the liquid as the main fuel, main product. If you want main product as a gaseous fuel, then we can go for gasification. And if you want to just burn it, get the thermal heat, and get that thermal heat, or for power application, we can completely burn it, right, in the combustor. So that's the route. All right. So here is again in briefly on gasification. So in this technology, we supply the biomass to the gasification reactor, and then we get the syngas. Now, as I mentioned, syngas has many different applications, and you can see here which primarily contains carbon monoxide and hydrogen as the main constituents. There are some CH4, acetylene, ethylene, some ethane. You might find some light hydrocarbons, for example, benzene, toluene, that could be possible. And then the tar, which is undesired contaminants, right? But if you want to burn it, it's going to give us energy, thermal heat. But for downstream processing to different products, we need to remove that because it's going to chalk, it's going to contaminate it is going to deactivate the catalyst also on the downstream side. And that's the reason, right, when we convert the biomass into syngas, our main focus is to get the carbon monoxide and hydrogen, which is commonly known as syngas, which now we can convert to transportation fuel for different chemicals, maybe for power generation, for steam production. We can also generate the fertilizer, and then we can also use in the consumer products. There is a application in hydrogen for oil refining, because in refinery process they need a lot of hydrogen, and here this from syngas they can get this hydrogen for the refining process, or we can get the synthetic natural gas from the syngas, which is then derived from different biomass resources. So there are several advantages of this process. Some are here. This technology accepts wide variety of feedstock. As I in my previous slides, I gave you there are several options available for the biomass, right, for to get the organic material, which we can convert through this conversion technology. So it accepts wide variety of feedstock. And then one of the good advantage of this technology is that because it occurs at high temperature and there is a presence of oxygen in this process, it converts all organic matters of biomass into syngas. So that's a good advantage, because there is no the unburned or unconverted biomass. You will see it. There is a char production in this process, so there is some unconverted organic matter will be there, but depending on the process parameter, it is possible to achieve right conversion of most of the organic compound into syngas, or some are maybe left in the as a solid form in the char. Again, one of the cheapest way to make renewable hydrogen, and then we can use that hydrogen for different application. Okay, now on this slide, I'm going to give you overview on biomass pyrolysis. So as I mentioned, there are different source of biomass available, and in pyrolysis process, what we do, right? So we maintain the desired temperature. We supply the inert gas to for the process, and that process can be, there are different sub-classification of this process, right? So for example, slow pyrolysis, as the name indicate, this process occurs at the slower rate. And then the fast pyrolysis, there is another term also, it says a moderate rate pyrolysis or moderate pyrolysis, which has speed in between slow and fast. The slow pyrolysis is basically also known as the carbonization process. Basically, we increase the carbon content of the feedstock by heating that feedstock at uh, moderate temperature or the lower temperature for longer duration of time. While in the fast pyrolysis, we do heat the particle or the feedstock at the rapid rate, so higher heating rate, and we do and then we do maintain the very low residence time. In the case of slow pyrolysis, it can be a day process, even more than that. But in the fast pyrolysis, it takes a few seconds. In that, we need to convert the particle into the liquid fuel. That's our main target in this process. So here are the some information on variables which influence the overall process. Ultimately, the type, the product quality, and the distribution of the product, basically the product composition. So that depends. Yes, go ahead. Do you have any question? All right. So variables, right? For example, feedstock type depends on, for example, if it is a switchgrass, some forest residue, all right, or some energy crops, municipal solid waste, right? Algae, sewage sludge. So depending on the feedstock types, the product is going to be different. and then the quality is going to be different. The quantity is also going to be different. Properties of the feedstock, right? How much carbon is there? How much hydrogen is there? How much oxygen is there? Moisture content. So it depends on those properties also. What is the process temperature, right? There was a range, as I mentioned before. So this process takes place between some temperature range. What temperature we provide, depending on that, it's going to give us the product and the product distribution. What's the process temperature? It also influences the product quality and the product yield. Heating rate, right? This is one of the important parameter. At what rate we are heating the particle of that feedstock. Particle size is another important parameter. Some of the pyrolysis process needs a very small particle size. Otherwise, the heat transfer is going to be limited in that process. The heat will not penetrate to the core of the particle, and we'll get in that short duration, which is a few seconds, right? Maybe 0.5 to 2 seconds or maximum 5 seconds. We need to convert the particle into the vapor, right? Then vapor will be condensed to bio oil. If you are not able to heat the particle during that limited time, very short time, then we'll have unconverted biomass, which is not good. So that's why particle size is also one of the important variable in this process. Residence time, as I mentioned, it's a very short as compared to slow pyrolysis, where it's a few hours to 1 day, even more than that. While in the fast pyrolysis, it's going to be few seconds. So for example, 0.5 to 5 seconds. Generally, it's around 1 to 2 seconds. But you'll see the literature where people have gone even up to more than 2 seconds too. So, and then the presence of catalyst, right? So uh, before, right, in the earlier, people have used performed this tech, explore this technology without the catalyst, but later on there has been many studies available where researchers have used different types of catalysts, even the special catalyst to improve the overall process to get the better quality bio oil, which is less complex to upgrade further to the advanced biofuels or the bio-based product. So there has been several studies using different catalysts in this area. So once we do the pyrolysis, this the different biomass resources can be converted to liquid fuel as the main product, and then we can go for further upgrading. So downstream upgrading, which we call catalytic upgrading or catalytic upgrade, where we can now convert this the crude-like oil, which is a bio oil, into biofuels, or we can also call it advanced biofuels. We can develop some high cost chemicals from this bio oil, or we can get the byproducts, for example, carbon fiber. There is a huge application of carbon fiber because of the weight. It has lower weight, it has good properties, good strength, mechanical properties, right? So it can, there are several heavy products which we are conventionally using. We can replace those conventional product by using this lighter carbon fiber. Okay, so there has been many studies on this area too. So so this is one of the good advantage of biofuel. We can utilize it through catalytic upgrading to produce the bioproducts. All right, so here is the biofuels, right, for whatever biofuels we produce, and there is a standard for that, which is ASTM D754409, which basically provides us the specification, right? What are the typical specification biofuel should have, right? So based on this, if you can maintain that, then this biofuel is suitable for different conventional applications. In this slides, we can see the different properties of bio oil as compared to wood, which is biomass. So we can see that bio oil has, when we compare the carbon, hydrogen, oxygen, and sulfur content. So carbon content, you can see that there is an increase in the carbon content of bio oil as compared to the raw material, the feedstock. that we can use to produce the bio oil. So it has 49 to 51%, and there is an increase in carbon content now. Hydrogen content also, you can see that almost pretty similar, right? Not much variation, but a similar range when we compare the bio oil and wood. And that's the reason, right? Because whatever hydrogen wood has, if you're not adding excess hydrogen in the process, at least we are anticipating that whatever hydrogen wood has should come to the bio oil, so that we have more hydrogen in that, right? Always there is 100% conversion is not possible, right? So there may be we are not getting even more hydrogen, but again, if we add some catalyst or hydrogen in the process that we call hydropyrolysis, we may add more hydrogen to the bio oil. So we'll see that in one of the study that I'm going to cover today, that we can use hydrogen also during the pyrolysis to enhance the hydrogen content in the fuel. Oxygen content, so wood has more oxygen, you can say that here, and we are getting significant part of that in the bio oil, which is not which we don't want. It is undesired oxygen in the form of complex compound, and many researchers since decade have been working on how we can reduce this oxygen in the bio oil so that we can make it more suitable, right, for the advanced fuel production. It will have better quality when we compare with the conventional fuel, for example, gasoline, diesel, kerosene, like that. And then sulfur content. So in biomass, there is no sulfur, so no sulfur in the bio oil. But if we get the, let's say in place of wood, if we go for a conventional feedstock, for example, coal has sulfur. In that case, bio oil will have sulfur content also. As content depending on biomass is slightly more. When we do conversion, there is a low S in the bio oil. It has moisture, a good amount of moisture in that, which we can separate by following some of the standard procedure to remove the moisture. When we compare the calorific value, which is per kg in megajoule, bio oil has, you can see that now little more dense, energy dense than when we compare with the wood. Wood has typically from 13 to 15 megajoule per kg, and here we can see that it's a 16 to 19 megajoule, or maybe a slight difference, but this is what the typical range we are seeing here. The viscosity here, it's a fluid now, so fluid has, this is 13 centistock at 50 degrees C. That's it's really viscous, and depending on if you want to use it directly, we may want to go for emulsification, or maybe heating it to make it more lighter so that it has better flowability, and then we can supply to the burner or combustion system to burn it for thermal application. A flash point at 66 degree C, and when we compare the acidity compared to wood, it is more acidic, right? It has several acids in this bio oil. So acidic value is pH is basically based on the pH. It has 2.5 pH value, while biomass has less acidic compared to that. You can see that the pH is 4 to 5.5. Okay, so here we learn about the typical specification of bio oil, and then we have compared the typical properties with the wood, right? Typical biomass, which is wood is really very ideal feedstock for thermochemical conversion, and that's why most of the studies, when you see that, you'll see the comparison with this ideal feedstock, which is wood. Okay, here we can see the process types and products. So we can see on the vertical axis, right, the categories. There are different processes: gasification, torrefaction. Torrefaction is one of the thermochemical process which also takes place under inert atmosphere, mostly nitrogen as a carrier gas. And then in this process, we heat the feedstock at low temperature, basically from 150 to 300 degrees C, in that range. And then uh, over the longer time, basically we get the solid is one of the product in this case, and then we also get a lot of gases in this. So And then slow pyrolysis, which is again, as I mentioned before, the carbonization process where we want more carbon in the form of solid product, so we get more solid in that. And then the moderate pyrolysis and fast pyrolysis. We can see that from the comparison, the blue one is the liquid. Gasification will have some liquid which is in the form of tar and some vapor, lighter vapor. And then torrefaction will have similar, slightly lower than the gasification. In gasification, we primarily get the gas. As I mentioned before, seen gas, that's the main product. We do get some solid as char and ash, so that's 10% or run about 10%, right? So slightly higher or slightly lower depending on the how efficient that process is. And then torrefaction has slightly more solids, it has gases and some liquid. Slow pyrolysis, the main goal is to get the more solid, so you'll say that more solid here, some gases, some liquid. In moderate pyrolysis, you'll get now more liquid, because pyrolysis now here our main goal is to get the liquid fuel, and then the some gases, some solid. But when you go for fast pyrolysis, which is again under inert atmosphere with a very short residence time, with and without catalyst, you can see that there is a higher liquid production, right? So the liquid is the main product here, right? So we are getting up to 70, 75 or even 80% liquid in the fast pyrolysis. And then the remaining other is the gas is the main subproduct, and some solid that depends on the how efficient that fast pyrolysis is, and that's going to give us some biochar, right, which has a really good value if you want to use that for soil amendment, or if you want to use that for to get the activated carbon, right? And activated carbon has many applications. So that's what you can see here, the how the product is distributed, right? Basically comparison between liquid, gas and solid product based on this different thermochemical conversion processes. So here now we can see the pyrolysis reactor types. So basically there are several subclassifications. So let's go one by one. So based on the process modes, right, what is the type of how the processes occur. So depending on if it is a short residence time, it is the right, it is known as fast pyrolysis, which is occur at high temperature in that pyrolysis range. It can, if it is if it is taking longer residence time at moderate temperature or at the low temperature range, it is going to categorize as slow pyrolysis reactor. And then, yeah, any questions? I'm getting the sound here. Let me know if you have any questions. And then it is also classified based on the movement of the feedstock. So the solid we supplied for conversion, is it moving or it's a kind of fix? So if it is fixed inside the reactor, it's not continuous feeding, then it is categorized as a batch reactor. Or if there is a moving bed, so right, as in that case, it is categorized as a moving bed reactor. And then it can be a rotating bed, rotary screw or kiln is the example for that. It may be a fluid bed, right? So if the bed is behaving like a fluid, then it can be subcategorized as fluidized bed or spouted bed or entrained bed. So that depends on the direction of the flow of the feedstock and the reacting that hot gases. And then based on the heat transfer modes, because this process needs temperature, and then how we are maintaining that temperature, or how we are supplying that heat, process heat, based on that it is also categorized as a direct heat transfer based type of reactor, or it can be a indirect type of indirect heat transfer types of reactor, right? In direct, we may use the inert material, a hot inert material. For example, in a fluidized bed, we use a sand, which is a silica sand, right? Or there is another inert material that we can use it, which is not going to react in the process, but it's going to provide the required heat. So hot inert material one can use, or the hot flue gases, right? One can use in the direct method, which is directly going to mix with the feedstock particle. In case of indirect heat transfer, we heat the reactor from using the external source of heat, maybe electrically heated, or maybe by using some flue gases, hot flue gases from some other sources, or the by burning some conventional fuel, or maybe the scene gas that we are getting from the pyrolysis process to supply part of the heat. So that can be used also for direct or indirect heat transfer for the pyrolysis reactor. And then pyrolysis, there are different designs, as I mentioned in the previous slides, right? So fluidized bed is one of the dominantly studied the design in this area. Then the another version of the fluidized bed is the circulating fluidized bed, where we are circulating the bed material. So in the fluidized bed, let me give you some more information through this diagram. So I want you to focus here on this diagram where we have the bed. In this bed, we have silica sand like this, or any other inert material, one can use it. So when we put the inert material in the bed, but if you don't supply the inert gas, which is nitrogen most of the time, so if you don't supply the inert gas, this bed is going to behave like a solid. And in the solid, even if you are using the let's say feeder, screw feeder, or conveyor system, if you want to supply the biomass, it is going to be very difficult to supply the feed into this solid bed. But what happened when we supply the inert gas, right? So we can see that now this inert bed, which is solid right now, but it will become like a fluid-like bed. So this bed will expand whenever we supply the required amount of inert gas, right? So at least more, we need to maintain the minimum fluidization velocity, and there is a calculation procedure for that. So slightly above that, again depending on the requirement. So when we maintain that, you can see here at the bed, this bed will expand like this. So when this bed will expand, when we supply the inert gas, now this bed is now behaving like a fluid. Okay, so in the fluid bed, now we can easily inject the biomass. Since this bed is hot, it is maintained at high temperature, there is a inert gases. Whenever we inject the biomass will start decomposing, right? Disintegration of the biomass particle will start, and then volatile metal will come out, which we want to quickly take out from the reactor by using this inert gas, right? Required amount of inert gas, and also maintaining the short time. And then when that vapor products comes out of the reactor, we want to quench it, we want to cool it, right? Basically we want to condense it as early as possible. So there is several studies on that side also, how quickly efficiently we can condense the vapor product to get the bio oil. As I mentioned before, this process also going to give us syngas as byproduct, and there will be some unconverted biochar, because we are maintaining a very short residence time to optimize the liquid, more liquid from this process. So that's the reason. So that's what the fluidized bed. In circulating fluidized bed, we take this sand, we use a very high velocity, we take this sand out, and then we use cyclone to collect the sand, which is heavy particles. So we collect sand back, and again we supply that sand back to the bed. So that's what the circulating fluidized bed we call it. And in entrant flow bed, we have typically we feed the biomass right in a smaller particle size from the top of the reactor. From the bottom of the reactor, we supply the hot gases, basically, which is going to provide the heat required for the pyrolysis process for decomposition. And then the hot gases which is coming out from the reactor, it will quench outside the reactor to collect the bio oil. In ablative process, it's basically the hot surface, a very hot surface, and the biomass particle is going to press against that surface by giving a short residence time. and that when it press against a high temperature surface, the volatile metal will come out from the biomass. In rotating cone type reactor, there is a cone which is rotating, and that takes the advantage of the centrifugal action, which has the sand and biomass particle is going to get mixed with the sand. There will be a good heat transfer between the sand, hot sand, and the biomass particle, which also occurs here in the fluidized bed and circulatory bed also. And then this is how the conversion takes place. In auger reactor, we use a screw. That's what the main design is. So by using the screw, we can control what's the feed rate, and then we maintain the temperature also of those auger reactor, desired temperature to get the bio oil from the biomass, right? We can use different biomass in this case also. And then there is another type of reactor which is known as vacuum, because here we maintain the vacuum basically by using the vacuum pump on the downstream side, right at the end of the reactor. We can maintain the whole reactor under vacuum condition, right? So lower pressure than the atmosphere. In that case, there is a pressure flow, and because of that, whatever volatile product produced under high temperature, again within the pyrolysis process range, that vapor product will come out because of vacuum, and then it will quench or condense by using the appropriate condenser to collect the liquid product. Of course, there will be gases, fuel, some scene gas, and some biochar solid product will be there in this process. All right, so this is about the different reactor designs available, and we can see here that we did discuss different variables before, but we can see that in this different reactor designs, basically what we are trying to achieve, that we want a really good gas solid contact, and all this different reactor will have different amount of or different degree of gas solid contact, right? So between the gas, hot gases or vapor, and the solid, the feedstock, it can be a sand also, inert material. Okay, if you have good gas solid contact, there will be good reactions, efficient reactions will be there. There will be good heat transfer. We want really good heat transfer and mass transfer in this process. We want a better temperature control also. We want the bed material or the reactor bed should be able to store good temperature thermal capacity, so that it can meet the temperature requirement or the heat transfer requirement. And we want appropriate residence times. If it is a fast pyrolysis, definitely we want to maintain residence times of few seconds, right? 0.5 to 2 seconds typically. In that times, we want to convert the biomass into vapor products and take it out from the reactor and then quench it, condense it. And then again, the processing capacity, right? Different reactor have different capacity, right? How much biomass, a typical biomass, it can convert per hour. Okay, so that's another consideration one can think of depending on these different types of reactor design. Okay, so here we will see now the pyrolysis process mechanism, and we can see here that so basically the biomass going to be converted to the primary product, right? So whenever biomass enter into the reactor under the presence of inert atmosphere, right? Inert gas, basically most typically the nitrogen, and then under the presence of high temperature, right, up to 500 degrees C, for example. Normally 500 degrees C typically people have used to study the pyrolysis. So the biomass is going to decompose, disintegrate into the primary products. At the same time, we will also get the primary char. And then what will happen, this primary products will go depending on the residence times. It is all these primary products will start interacting with each other. All those reacting agent, right, reacting product will react to each other, and they will then go to participate, right, which we call secondary reactions, and that will produce secondary products. During this time, then there is a production of secondary char, right? The solid residual, we call it secondary char. So there will be some addition of char again. And definitely we don't want this secondary char, or we want to control this secondary product. 100% control is difficult depending on the process time, environment, right? People have been trying to optimize it, but if we can control up to a great extent, right, we can minimize the secondary char, or we can have a better product distribution. Okay, I'll come to on different types of product, favorable product, right, desired product which we are looking. I'll come to that later on. So this is what the typical mechanism we can see, that right, there will be a primary reactions which will give primary product, which is going to react further, and that will give a secondary products. So we'll get primary char also and secondary char, which is undesired. We don't want that. We want more bio oil, liquid fuel, but we do get some solid fuel also. So again, depending on, as we have discussed before, depending on the overall process conditions, right, there are different variables, how we are maintaining those variables. A biomass decomposes via different conversion pathways, right? If different parameters, the conversion scheme is going to be different, conversion mechanism. And if it is different, then it's going to yield different pyrolysis products. So you'll see different amount of liquid, different amount of gas, different amount of solid. Even in liquid also, we will see different compounds, different types of organic compounds will be there depending on the process parameter. All right, so now here let me give you some more information on the biomass pyrolysis before I come to that. As I mentioned before, biomass contains lignin, cellulose, hemicellulose, right? So if you want to understand the pyrolysis of biomass, which is a really more complex, right, in terms of composition, it would be more better if we can explore the pyrolysis of lignin alone, pyrolysis of cellulose, pyrolysis of hemicellulose, or mixture of one or two, how it is going to, what kind of product it yields at that process temperature and the atmosphere. So if you get that information, then we can couple all those information, individual information, combine them, and we can have a more better estimate or information about the pyrolysis of a whole biomass, right, which compose lignin, cellulose, and hemicellulose. And that's the reason you'll find many fundamental studies on the pyrolysis, where people, instead of using the whole biomass, people have researchers has used lignin as a model compound to represent biomass. There are many studies where they have used cellulose because it has different compound compared to lignin. Pyrolysis of cellulose, and then how it is going to decompose into bio oil, or what kind of oil product we will have, or gas and the solid. Similarly, there will be some studies on hemicellulose. So in lignin, in case of lignin, it is the most stable component of the biomass compared to cellulose and hemicellulose. It is slow, it degrades slowly or at the slower rate if the temperature is 200 degrees C or lower than that. But if we increase the temperature from 280 degrees C onwards, let's say in between 280 degrees C to 500 degrees C, the lignin decomposition is going to be rapid. So then in this temperature range, it degrades rapidly, but at lower, it's kind of, it shows good stability at low temperature. Basically, lignins, when we do lignin pyrolysis, it yields more char as compared to that we see in case of cellulose pyrolysis, and the low heating rates results even higher char production. So it's very important when we go for lignin pyrolysis, we need to maintain the proper appropriate temperature so that we don't get more char, because in pyrolysis our main goal is to get liquid product, liquid fuel, right, bio oil. Compared to lignin pyrolysis, if you see the cellulose and hemicellulose pyrolysis, this occurs generally begins about 250 degrees C, not that high temperature, what we have seen in case of lignin. Generally at around 350 degrees C temperature, the cellulose rapidly decompose in pyrolysis process. And here primarily you're going to get the volatile and tar as main product. And of course there will be some char, but it's going to be lower than what we get in case of lignin. Lignin will have more char production. That's a solid byproduct. Again, for hemicellulose, comparatively, the semicellulose compared to cellulose, it occurs at low temperature, and again, it will have the similar product range. Again, some char will be there also. Now, let me, after so far, I gave you the overview, right? The broader perspective on this area in this field. Again, more focus was on the pyrolysis, and we can see that there are still several challenges do exist even as of today also, and many right researchers across the globe throughout the world, they are working on these areas to further again optimize the overall process, so that we can have use this technology for at the demonstration scale or even at the industrial scale. That's the overall goal. So first of the challenges, we can see that again with the biomass feedstock, there are different biomass resources available, as we have seen before, and those different source of biomass generally provides us feedstock with different properties, right, or different physical chemical properties. So we are not getting the, if we are getting the biomass from different resources, there will be an inconsistency in their properties. So if we have designed the reactor, if we have optimized everything from the reactor side, now we need a constant quality input. And if our biomass feedstock has inconsistency, then it is going to affect the reactor performance. So that's the reason there are good amount of research going on how we can optimize the feedstock by doing some pre-processing, right? For example, drying, cutting the biomass in the precise size by torrefaction, right? Just to remove some of the vapor, right, to get the desired quality or to have more carbon in the biomass, removal of some unwanted component from the biomass. When we get the mixture, for example, in case of municipal solid waste, it has some inorganic compound too. So it's better to separate the inorganic compound from the biomass, so that we have the better quality, consistent quality feedstock available throughout the year for the conversion process, and that is going to give us a reliable, consistent performance of the reactor. So this is one of the challenges right, people are working on. Another is that at the conversion steps, still there are many different reactors people are exploring, getting different efficiencies, different performance parameters, and still the bio oil that we are getting, it has lots of oxygenates. So oxygenates, basically it has oxygen in that. There are several compound, organic compound which has oxygen molecule in there, right? So oxygen atom in that structure, and we don't want oxygen in that. We want to remove most of the oxygen from the bio oil to make it suitable for advanced to use it as advanced biofuel. Then we have char, depending on the type of reactor or the pyrolysis modes. Bio oil might have lower char or might have higher char. So how to optimize that? Tar is another, that heavy polyaromatic hydrocarbon. So we don't want that. It's very complex, and so we want to remove that also. We want to minimize that. Sulfur is another thing. If our feedstock has sulfur in that, that's a chance from when we use a municipal solid waste, it might have some sulfur. So we want to remove that. We want even want to remove the nitrogen from the feedstock, because then it is going to produce the compound which has nitrogen on that. So depending on the temperature and availability of oxygen, it might give some NOx production also, which is generally mostly you'll see in case of gasification and combustion.
but it might be in this process also if there is oxygen available at that high temperature. And then bio-oil upgrading, let's say we got the main product bio-oil. Now we need to upgrade that. So in that case, we need to match the downstream process requirement, because different upgrading process require different type of input conditions, right, of the bio-oil, different properties too. So that's another challenge that people are working on. There are different, even people are trying special types of catalysts also, which is again costly. And then there is a lot of work still need to be make it economical, so that we can do efficient, effective catalytic upgrading of bio oil to advance biofuels or bioproducts or biochemicals. Gas cleanup is another problem. We do get gas as byproduct. If there is a significant production of gas, it will have some tar also. We want to clean it. We want to upgrade the syngas if it do not have the desired value. So it do need appropriate downstream processing technology for that. Then again, process optimization and integration with the existing application. That's another issues, and people are working on that. Uh, okay, in this area. And then technology success, when we see this from this angle, definitely we are looking this at least at the demonstration stage, all right, for longer duration, and then going beyond from that level to the industrial level, right? So we can use it for different industry applications. So considering this challenges, right, I have been working, as I mentioned before, since over 16 years, and there are several goals that I have been focusing so far. The overall goal is to strengthen the fundamental and applied research in biomass thermochemical conversion areas. My primary focus is again the gasification, pyrolysis, and then with that we are also hydrothermal liquefaction. That's another area that one can I'm also focusing on that side too. Then the another goals is to develop the efficient and economical biomass conversion technology that can take right, that can utilize different diverse biomass resources available, and then it can it can produce, right, reliable, consistent quality bio oil, and then the bioproduct too. And then to provide the educational and research training, right, this is again what I'm doing today. It's a part of educational training and research, sharing the information in this area. Okay, so that's one of the goals of my research. And then if we see the specific objectives, so in that to characterize the properties of different biomass feedstock, there is wide variety of feedstocks are available, and we need to study the properties. What is the variability in that properties, how variable those properties are, can we tune up to get the consistent quality feedstock, so that no need to worry, right? We can provide good quality feedstock throughout the year. So that was the this one of the objective. Another objective is to study the study effects of biomass properties, right? The properties that we are studying here, what's their effects of those typical biomass properties on the performance of the reactor. Again, there are different reactors, so how this properties is going to influence the overall performance and the product quality and quantity. And then model the biomass conversion process. So I have been also involved in developing the modeling of the chemical conversion process. So that's also work, because once you develop the precise model, then you can validate different biomass feedstock, and then you can optimize the time, efforts, right, the money, right? There are several things that we can optimize, we can save. And then to develop an efficient and economical overall process, right, so that we can make this technology feasible for different commercial applications. So with this, now I'm going to talk on one of my research study that was on catalytic pyrolysis of biomass lignin. And here I'm going to focus now on lignin pyrolysis. So we can see here that this is what the structure of typical structure of lignin looks like. And you can see that it's a good source of aromatic hydrocarbons, right? If you see that petrol, the gasoline, diesel, right, which has a lot of aromatic compound in that. So it has basically chemically it has alkanes, aromatic compound, right? Or in other words, paraffins, olefins, all those compounds are there. And you can see in lignin, all those compounds are there, but it's connected. It's not separate. And it has a lot of oxygen in that, right? You can see that a lot of oxygens are there. We don't want oxygen when we want for our ideal biofuels. So yeah, it's a good source of aromatic hydrocarbons which we are looking for. And when we go for catalytic deoxygenation, it's kind of challenging because of this complex structure, right? Because it's very complex structure, where to cut, right? Where to, and then when you disintegrate again, there is a chance of secondary reaction it combine again, right? So there is several complex process takes place. So basically that's end up in low conversion efficiency and then high solid yield. We don't want higher solid because it's undesired. We want more liquid. That's our goal. So this study, let's even in addition to this complex structure, lignin has different amount of this H unit. You can say that this is what the H unit looks like, then S lignin, and then G lignin. These are the typical component lignin will have. So if you see that there are different types of feedstock, for example, hardwood, softwood, herbaceous crop. So in that case, all these different biomass species will have different amount of H, S, and G units. And basically that's going to create another hurdles, right? Another complexity when we want to convert lignin into the biofuels, right? Aromatic hydrocarbons. So that's another challenge is depending on the biomass type because it has different properties. And then most of the when we go through the literature review, uh, most of the technical lignins that researchers have explored that study those lignins basically do not accurately represent the natural lignin in the biomass. Okay, so uh, if we have developed the lignin, if we have produced the lignin via milled lignin process, that is again which is identified as basically the lignin derived from using the milled process represent more closely the natural lignin present in the biomass. So in our study, we have used lignin derived from milled lignin process, that typical process, and that's why we can our one of the advantage in this study is that the lignin that we have used, it was very close to the natural lignin present in the biomass. So then if you see the catalytic, there have been many catalysts people have studied in this area, and here are the capability of some of the catalysts of interest. So this HGSM5 or GSM5, which is a zeolite based catalyst, it is really very good in cracking and deoxygenation processes. And then it do not require hydrogen for the process. It occurs even at low system pressure, so we do not need a high pressure for conversion, for catalytic upgrading or conversion. On the other example, nickel catalysts are also have been extensively used for hydrogenation process or for cracking process. So when we call it hydrogenation, we add hydrogen, we saturate the that organic compound, and in cracking we convert the higher molecular compound to a lighter molecular compound which is desired. So that's what the cracking process does. And this process again requires hydrogen environment and high pressure. For that, there is a molybdenum oxide catalyst, so MO3 catalyst. People have used that, and it is really good on hydrodeoxygenation. So it when we supply the hydrogen, it deoxygenates. Remember, I told before that we don't want oxygen, so we can remove some of the oxygen by through this process. It also helps in dehydroaromatization, so it will build the aromatic compound using this catalyst. And this process can occurs at low pressure under hydrogen atmosphere for this type of catalyst. So what we did, right, these are the single catalysts, we can see that, right? So we thought that if we can merge, right, if we can combine one or two of these catalysts as a bifunctional catalyst, for example NiGSM5, right? GSM5 has been widely studied, so we wanted to combine NiGSM5 and then MO3 GSM5, for example. If we can combine these two, we can develop the bifunctional catalyst, and then from the bifunctional catalyst, then we can have both cracking and hydrogenation benefit. So with that, then okay, so the objective of this study was to study the catalytic pyrolysis of different mean lignin in low pressure, which is near to 1 atmosphere, under helium and at H2 atmosphere, and to investigate the effect of bifunctional catalysts on lignin conversion compared to single geolite conversion, right? So we have compared bifunctional with the single geolite catalyst, and then to investigate how lignin composition in biomass affects conversion outcomes. So with that objective, here is the details on research approach that we have used. So this is the fundamental research. So what we have used the tandem micropyrolyzer, right? So we use a very small amount of quantity of biomass here in the micropyrolyzer, which is a lignin, mill lignin. And then we maintain, in first case, we maintain a helium atmosphere, not nitrogen. And then in the second run, we have maintained the hydrogen as atmosphere. In case of hydrogen, since hydrogen was available, it influenced the overall process, and then we'll see that what product we obtain. So once we pyrolyze the liquid, now vapor is from the reactor, then we directed all those vapor liquid to the XC2, the catalytic bed. In this catalytic bed, we have used these three different catalysts. So there will be three conditions. We have used three feedstock. Those are mill lignins. So for example, corn stover mill lignin, which is a herbaceous crop, the feedstock. We have used low blue leaf pine, which is a softwood based lignin, and then red oak, which is a hardwood based lignin. And then we have used three types of catalysts. We use SGSM5, which is a single catalyst for comparison, and then we use 2% loading of MOO3 in GSM5. That's a bifunctional catalyst, and similarly 2% loading of nickel in GSM5. That's the second bifunctional catalyst. The catalyst to biomass load ratio was 20:1, which is here. And then you can see here the temperature that we studied in this process was 600 degrees C here for the lignin one, and then 600 degrees C for the catalytic bed. And then we maintain helium atmosphere and also H2 atmosphere near 1 atmosphere condition. As I mentioned before, mill lignin represents natural lignin in biomass. So that's what we wanted to study through this research objective. Now we can see the overall results here in this slides. Pardon me for this heavily loaded slides, but I have purposely kept all the data in single slide so that we can have a better comparison. So we can see that here the lignin, the corn stover herbaceous lignin, then log pine, which is a softwood lignin, and then red oak, which is the hardwood lignin. And we have data for the helium environment, which is inert, and then H2 environment, which is a reducing. You can say that hydrogen is going to participate in the reaction, helium is not. And we can see that if we compare the corn stover herbaceous liquid, the lignin, we have all these three catalysts, SGSM5, then bifunctional catalyst, MOO3 base, and nickel base. And you can see that here, if we compare the aromatic compound, which is the desired compound we are looking for, what we found that it's 11.11, then 9.7, 10 around under helium atmosphere. Then alkanes and alkenes are also there. You can see that the distributions, the gases, lighter gases compound, right? CO, CO2, catalytic coke also, right, which you don't want, but it was there since we have used the catalyst. So at 16.9, 17.8, you can see that. And then you can see the total sum, right? Some are the losses, and then some because of the complexity, some we are not able to collect that. So this is what we collected here. And we can see that clearly here under whatever we have obtained under helium, when we see that similar result under hydrogen environment, you can see there was a significant increase in the aromatic compound, right? What we are seeing here in for case of Constover, which is 11, we found 20.5. So that was almost when based on the available data, the increase was 30 to 145% depending on the type of lignin and catalyst, right? Similarly, here also we found more aromatic. Here also we found more aromatic compound, right? So in this fundamental study, we found that the hydrogen environment contributed significantly to improve the aromatic compound. And then if we consider the catalytic coke yield, it also reduced significantly, right? You can see here 16.9 while we are seeing 9.3. Similarly, here you can see that coke was also reduced, right? In all the cases, there was a significant reduction in the coke. That's really good. Even the pyrolysis char, that's a solid product, there you can see here, it is also reduced slightly, you can say that. Mostly in the case of hardwood, you'll see a significant decrease in that side also. So overall, we found a really good data in this study. Here is the product selectivity, right? Remember, one of the important thing that how selective the process is or the catalyst is for the desired product, right? We want more aromatics, right? So in that case, if we see here under helium atmosphere and under hydrogen, which is BTEX is the aromatic compound which we want, and you can see that all under the helium atmosphere, the Ni nickel base has more PTEX, slightly above 60%, but when we supply the hydrogen, the molybdenum base MO3 MO3 GSM5, right, which is here, it shows a significant increase in the aromatic selectivity, right? It selectively produce more aromatic compared to other two catalysts, right? So that was a really good results we obtained here. When we see the aliphatic selectivity, you can see that under helium, right, more methane was produced, and then in case of we can say that around 15%, if we do the 10 to 15%, that was the range. But when we supply the hydrogen, the nickel based catalyst was right that the hydrocracking, you can see that that's a clear indication that a lot of cracking is going on in presence of hydrogen for the nickel GSM bifunctional catalyst, and that's why we saw a really good increase in the aliphatic selectivity, right? Particularly the methane was very high, right? You can see that close to 50%, while here it is around 10 to 15% for the studied three catalysts. So that was the selectivity change we found in this case for the Constover mill lignin. If you see the lobularly pine mill lignin, we have the similar data, right, where MOO3 outperformed the other two catalysts. It has better selectivity for the aromatic compound, and similarly it has given more methane as in the hydrogen atmosphere as compared to that we found in under helium atmosphere. Similar thing here you can see for the redox. Here also we found that the MO3 based bifunctional catalyst produced right around close to 85% selectivity for the aromatic compound, as that we obtain around 60-65% in case of helium atmosphere, but here we got a higher percentage. So that's, and then methane, of course, are very similar. Here the methane was slightly higher for the redox, which is the hardwood lignin. We did studied some phenolic monomer, because in lignin these are the typical monomers we'll find in more quantity. So we wanted to see that if we, instead of lignin, if we go in further in detail and if we study only monomer, right, for example phenolic monomer, phenol or glycol, how it is going to, what will be the conversion. So in that case, we found that you can see here that this MO3 gives us a significant improvement in the conversion. And then when we see the glycol, it was in all the three catalysts studied, gave almost like close to 100% conversion in that cases. And then here you can see the yield, which is the converted phenol, the carbon percentage, and you can see that MO3 gave the highest carbon conversion. That's really good. and really good aromatic production, high production. And if you see the selectivity, phenol has, you can say that the benzene was the highest, right? Selectivity MO3, and then followed by the nickel-based bifunctional catalyst, and then the HGSM5. The HGSM5 also had higher selectivity before the PHS, polyaromatic hydrocarbons, which is not desired. So you can see that the bifunctional catalysts perform really well in that category. And here are the similar results for the glycol H2. Okay, and then you can see that MO3 really perform well as compared to the other two catalysts, and also it has a higher aromatic selectivity as compared to the other studied catalysts. So to conclude the lignin study, we found that the distribution of pyrolysis product significantly depend on the biomass species, right, from where the lignin was derived. Compared to helium atmosphere, hydrogen atmosphere showed a considerable improvement in the aromatic compounds and the selectivity to the desired compound in the bio-oil as compared to helium atmosphere. HGSM5 produced the highest total aromatic yields for all lignin, which was the single catalyst, but selectivity point of view, MO3 GSM5, the bifunctional catalyst under H2 resulted in the highest selectivity for the BTEX, which is benzene, toluene, ethyl benzene, and xylene. So that was the desired product, and it also resulted the lowest coke yield, followed by the NiGSM5, which is another bifunctional catalyst, and then the HGSM5 in this study. H2 environmental promoted alkene production also that we found for phenolic monomer studies. We found that MO3 GSM5 gave the highest aromatic yield, followed by the NiGSM5 and the HGSM5. Overall, MO3 GSM5 was found to be effective based on our anticipations, and then it performed really well for lignin conversion. So we are still working in this area. So biomass catalytic conversion to selective production of the desired product, that's one of our target. Then lignin based biopolymer production, that's the carbon fiber, and then production of some value added bioproducts or biochemicals, that's also our future research focus. And then modeling of the MSW conversion through thermochemical conversion processes for the production of biofuels and bioproducts. So these are some of the future research focuses, and I want to acknowledge the financial support for the lignin study, and that was from ExxonMobil. And with this, I am done for my presentation. I really appreciate your time, and now I would be happy to answer if you have any questions.
Thank you so much.
Thank you so much, sir.
You're welcome.
Participants, if you have any question, if you wish to interact with sir,
Yeah, go ahead. Yeah, unmute your microphone and you can ask a question. Yeah, if you do not have question now, you here is my email address, right? You can feel free to contact me if you have any question later on. I see raise hand, Jigar. Do you have any question?
Sigar sir, do you have any question or?
Yeah, I'll do that. I'll send the feedback form.
Yeah, there are many literature you will find on chemical properties, on selection of biomass. Basically, I would say that depends on the what type of process you are focusing, because if you're looking for, let's say, a pyrolysis process, what type of reactor, and then once you decide the type of reactor, what process conditions you want to maintain. Basically, that also depends on what type of biomass locally available or the biomass you want to study for that process. But if you have biomass decided, then you can decide the type of reactor process conditions. But so this is kind of you can work from both sides, right, from left to right or right to left. And for properties wise, you will I would say go for Google search, or on sciencedirect.com you will see a really good amount of material on for different biomass. Yeah, I do have in my data bank a lot of paper also, right? Yeah, so one question I got, the raw material for biomass is natural source. That's true, right? Except that municipal solid waste, right? So the source is affect the property. That's correct. How we include in analysis, right? So basically, if you are measuring the properties through proximate analysis, ultimate analysis, or to measure the constituents of lignin, hemicellulose, and cellulose. There is a typical standard procedure you can follow that to know that, because that you cannot change it, right, in the natural form. But once you have the raw material, then you can go for pre-processing steps. If you want to convert, if you want to uh, tune up some of the properties within the desired range. For example, some biomass might have very wet, it has a lot of moisture, then we can go for drying, right? You can do a sun drying for a few days, keep it outside, or we can have the forced drying, and we can maintain the desired moisture content of the biomass. We need some for the process. So that's one example. Typically, if you want more carbon in the product, then the raw material, you can go for a carbonization process, right? Basically, I would say torrefaction. So you can go for torrefaction, which will remove the moisture and some vapor, and then after that, torrefied biomass is going to be really good for conversion process. So that's another example. So yeah, different biomass naturally available will have different properties. That's one of the issues, right? We are getting inconsistent properties, and we want to make it consistent. So for that, we need to do at least some initial pre-processing to get the desired properties. I hope did I answer your question? Okay, you are welcome. All right. So if no question, I'm concluding my presentation here, right? If you have any questions later on, just let me know, right? You have my contact email here, so feel free to contact me. All right. So with this,
Okay, thank you so much, sir, for giving a wonderful presentation
mhm.
and giving a knowledge about the different pyrolysis processes and the parameters which are affecting the pyrolysis process, uh, which will be, uh, you can say, a scope of for the new researchers. So, on behalf of our institute and the Department of Mechanical Engineering, I'm heartily thankful to you for providing your valuable time from your busy schedule. Thank you so much, sir.
Yeah, you are welcome. Thank you.